Yeah, no time yet today.
Okay, everyone, if we can put our phones away, we're going to jump into things today. Here's kind of our outline of where we're looking at, though. So, first off, something that you should understand in general, and then also just considering this year's circumstances. So for me as a teacher, this is my list of priorities of like, okay, when I need to get things done, how I always do that. My first priority is making sure our lesson each day is as good as it can be, because that's my job is to teach you. Okay, so when I spend my time, that's my first thing I do. The last thing I always do is grade late work. That's the last thing on my to-do list because it's already late, and so it just gets pushed back. It will get done eventually, but in case you're wondering with things that get turned in late, if it hasn't been graded yet, you can always ask me about it, but most likely it just hasn't been graded yet. Also, considering the circumstances of things this year, of me being an in-person teacher and an online teacher at the same time, and that is taking a lot more work on my part, it's making late work get even pushed back even more. So I apologize for that. If you're waiting, it will get done. You can always ask, but normally that's just the case. In terms of where we're looking though, I will make sure that everything is in by this Friday so that you can see by next week, because if you weren't aware, the term ends next Wednesday. Fun fact. It's also fall break, so that's a positive note. But just kind of be aware, if you're wondering where you're sitting, you'll know by this Friday. Okay, your add-on projects are in, so you can, if you haven't checked those out, they did go in as test points, which means for most of you that actually was a good thing because you did a great job on your project, especially those of you that turned in early, you got some extra credit points, so that helped out your test category, which in this class means a lot. Okay, where we're looking for in terms of this term and this unit is we are going to take the Unit 2 test on Friday. Okay, so today in a sense is the last day we're learning something new for this unit. On Wednesday we'll do a review game for it and then we test on Friday. But keep in mind that if there's questions you have about any of the ICAMs we've already covered, so we've already covered 2.1 through 2.3. 2.4 we touched on, but it will fit in today's lesson as well. But if you have questions on any of those things, get them figured out before Friday happens, okay? What that means is if you are needing to retake or wanting to retake the Unit 2 test, you will have time to do so, it's just not a lot of time. Because obviously once again the term ends Friday. So if after taking it, because you'll get your score back instantly, if you want to retake it, then you'll probably want to start corrections over the weekend so that you can retake it Monday or Tuesday of next week, okay? Any questions about dates or things, as I can't believe first term is like already done. I feel like I just met you guys. But okay, so here's our objective for today. Okay, so for ICANS 2.5 and 2.6, notice there's two key things, and they're two different parts of ICAN. We need to be able to explain and predict 4 different trends. Okay, now what trends are is they're patterns on the periodic table. We're going to look at the general trends of terms of is it increasing or is it decreasing? So number 1, you need to be able to predict it, or you could choose to write that down on your note card. Once again, remember you'll get a note card for the test, but you'll need to know how to do it some way. But then the biggest thing is you need to be able to explain why that's happening. Why is it getting bigger or why is it getting smaller? From my experience and my opinion, if you can do this, that just makes sense. You can explain why it's getting bigger, you know it's getting bigger. So I want you to really focus on the explaining side, because then the other side is like, oh yeah, that's very logical. Okay, so what we'll be doing is as we go through the lesson today, is I will be having you with your table buddy make predictions about the trends before I tell you what it is. I can't force you to, because that would be like mind control. Okay, but I can't force you to actually think about it. But I highly encourage that you try to make a prediction, even if you're wrong, because your brain does really magical things when you make mistakes and you recognize the mistake. Your brain says, oh, that didn't work, so don't do it that way again. But if you're not afraid to make a mistake, then your brain never has that chance to learn not which way not to go. Okay? So don't be afraid. You're only going to lose smiley faces today, which, well, you won't lose any, you just won't get some. But if you participate, you'll get plenty. Okay? All right, so I think, tell me if this matches up where we left off last time. Does that match up, or do we need to go back a little bit? I think actually we need to go back.
Yeah, we need to go back.
We need to go
Yes.
to this. Does that look better?
Yeah.
Periodic trends are due to, right, are we on the top of the page? I guess there's no page number. But this one?
Yes.
Okay, that's where I had marked, but I wasn't sure. Okay.
Did I start the camera?
Yeah.
Okay, so there's an overarching theme for the 4 trends we're going to learn. So this will make it even simpler. Okay, is rather than memorizing 4 things, it really goes down to one key fact. Scientifically, you don't have to really know it by name, but it goes down to what is known as Coulomb's law. Coulomb's law is the law that tells us, in simple terms, that positive and negative things are attracted to each other. Right? I think that's kind of common knowledge by this time at your age, right? You know that if something is positive, something negative, they are attracted. Okay? This is a scientific law that tells us that. Now there's 2 things that affect Coulomb's law. And this is outside of chemistry, anytime you're dealing with positive or negatives. Okay? The positive and negative force is based on 2 things. It's based on the magnitude, or you could also say the strength, meaning the more protons and electrons you have, the greater the force. Makes sense, right? A bigger magnet is going to have bigger force. Okay? The second thing is all about distance. The closer your positive and negatives are to each other, the stronger the force between them is going to be. So that relates all to the size. Obviously, a smaller atom is going to have greater attractive force than a bigger atom. Now, when we're talking about positive and negative, let's grab the model here to talk about it. Turn to your table buddy and remind them, what is the charge of an electron? Tell them. If you told them negative, you can have a smiley face. Okay? So when we talk about this negative and positive force, we're talking about the relationship between the electrons in an atom and the protons in the nucleus. Yeah, last year. Crazy how they welded it themselves, actually. Yeah. Okay, so that's what we're talking about, that positive and negative force between the electrons and the protons in the nucleus. Okay? Now, maybe it comes up later, but I'll say it now. The name of that force, or the abbreviation, is we call it the effective nuclear charge, which is symbolized as a Z with an EFF for effective. Okay, so this is the symbol for the effective nuclear charge. So as we go throughout the lesson today, anytime I say Zeph, this is what I'm referring to. Okay, so the Zeph of an atom is the strength of its nucleus. The higher the Zeph, the stronger the nucleus, the stronger the force. Okay, so in all of our trends today, when you're trying to think about, okay, why would this be? Think about positive and negative forces. Okay, now as we look at these trends, we're going to be looking in 2 different directions. We'll be looking vertical, so on a periodic table, up and down, what's happening, as well as we'll be looking left to right. Okay? The biggest thing, once again, is to recognize that it all goes back to that force of attraction that is happening between them. Greater distance means less force. If it's closer together, then there's more force. Okay, so we'll also be looking horizontally across the rows of seeing what's happening. Now what we'll do is we'll take our up and down and left and right and then translate it into an overall diagonal pattern. That's the way it simplifies it into one trend line. So generally speaking, when we look at the periodic table, atoms that are in the upper, I would just draw, sorry, I didn't make this, I would choose, don't draw both arrows, that's confusing. I like to just pick one. So I would just draw the increase arrow only. Okay, so as I go from this corner of the periodic table to that corner of the periodic table, Zeph is increasing. So you're going to label up there as the highest Zeph, and down here as the lowest. Okay, well, sorry, did everyone get that? Okay, now one other thing as we, and this actually goes to your ICANN of 2.1, is identifying the number of valence electrons in an atom. Okay, so once again, we've introduced this word before, but valence electrons are the electrons on the outermost ring. So when you build a model, how many electrons on the outer ring is your number of valence electrons. Now, one way you can identify it is by its electron configuration with the S and the P only. Okay? So for nitrogen, that tells us, because there's 2 in the S, 3 in the P, that it has 5 valence electrons. There's some space down at the bottom where you can just write some of these examples. You don't have to write all of them once you feel like you've got it. Okay, same thing, oxygen has 2 in the S and 4 in the P, so it would have 6 valence electrons. And then our fluorine here would have 7 valence electrons. Now take a second, everybody, and I would pull out your periodic table that you can write on yourself if you have it. This is a pattern you might want to put on there to have as a quick reference. You could also put it on your math one if you want, like the one that we colored. So, like we said, the valence electrons are only in the S and the P orbital, because the D and the F don't get put on the outside. They get put on the inner limits. So instead of, if a question were to say, how many valence electrons does oxygen have, instead of having to write out the configuration, there's a shortcut you can use by just looking at the periodic table. Okay, I'm going to draw a rough one here so that people who are watching at home can see what I'm talking about. Okay, can someone by raise a hand remind me where's the S orbital? Or everyone point with your finger. Where's the S one at? Very good. Okay, so the S is here, and then the P is over here. So, since the valence electrons are only in the S and the P, if we count just the S and the P vertically, you can find the valence electrons. So oxygen is located right, oh, I didn't draw enough lines there. So here's our little oxygen. So the number of valence electrons goes 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 6 valence electrons. So instead of having to write out the configuration, you can just count to find how many valence electrons something has. This might be why in earlier science classes you've learned about the octet rule. Has anyone raised your hand if you've heard of that before? In other science classes, kind of. It's all because of this idea of 8, which we'll talk more about as we go. Okay, for smiley face, don't say it out loud. Just think in your head. Find for me how many valence electrons does aluminum have? Don't say it out loud. Just think in your head. Now take your hand, put it underneath your chin, and show me on your fingers how many valence electrons aluminum has. Okay, if you show me 3, you can have a smiley face. You're correct. And that's pretty much what the questions about 2.1 are going to be like. Is they'll just be like, how many valence electrons does this one have? So, any questions on that? Okay, let's jump into, one thing just to kind of be aware is obviously things that are in the same column, that's why they have the same number of valence electrons. Is because these are all 6. It's because we're only counting the S and the P's, even though that one has 10 in the D, they don't count towards the valence shell. The reason why they don't count is notice this is only level 3. It's not the outside level, so they're not valence electrons. Okay, first trend. That's kind of a trend, I guess. Okay, okay, so as we look at our trends, a few things to be aware of. Okay, a full octet is the most stable configuration. So when atoms have 8 electrons in their valence shell, they're the most stable. Ions are our charged atoms created when electrons gain or lose electrons. So back like in last unit, we talked about something having like a -2 charge or a +3 charge. Those we classify as ions. Okay? Only the valence electrons are involved in reactions. That's why when we shortcut configurations, we just group all the core ones together. Okay? Reactions happen because an atom doesn't have a full octet yet. If something already has an octet, it's very resistant to react or bond with things. And then valence electron behavior is based on their attraction to the protons in the nucleus. So once again, going back to that positive and negative force. Okay, everyone good? Okay, the first trend we're going to talk about is the pattern of atomic radius. Now, when we use the word radius here, we're talking about just like you would in math, right? So, what's the radius of a circle? There you go, I see everyone drawing there, right? It's from the middle to the outside. So, an atomic radius, in a sense, is the same thing, right? So, that's a radius. An atomic radius is measuring from the middle of a nucleus to the outermost electron. And yes, this is something scientists can actually physically measure, which is crazy because atoms are so small. They don't do it by the use of a ruler. It takes a little bit more work than that. But we actually know physically in measurements, the measurement they use is a picometer because it's so small. You have to cut up a meter a lot of times. But that's what it's telling us, okay? So let's first look left to right. So as I go from the left side of the periodic table to the right side of the periodic table, what do we see is happening to the sides? That got typed wrong. Does that say increase to the left? That should say, does that? Oh, to the left. Thank you. I'm being mirrored image. So they're talking about this way. Okay, as I go from the left to right, we see that atoms are getting bigger in size. Okay? Up and down, we see that as we go down a group, generally speaking, they're getting bigger in size. So let's start thinking, let's go up and down. That one's a little bit more logical. So turn to your table, buddy, and take 1 minute and see if you can come up with a reason of why would francium be bigger than cesium? Why when I go down, do they get bigger in size? Ready, set, go. Tell everybody what you think.
Wow, because they have more shells. Shells, more electrons than entirely matter. Because carbon has more lithium. But they have more shells. So, these You're 90% shallow.
Okay, anyone willing to share their thought of what? Hayden, let's hear it.
I said because the atomic number is increasing.
Good reason for sure. Have a smiley face for that. So he said the atomic number is getting bigger, so it makes sense that the atom should get bigger. Anyone else have another thing to add? Rachel?
Isn't it when you go down another layer, another ring of electrons forms? So
Very good. Yeah, each one of these numbers is a new entire ring. So as they're getting bigger, it's not just packing onto the normal ring it's already on, but you're adding a whole new entire ring of electrons. So obviously every ring is going to increase that orbit. Perfect. That was my face, Rachel. Okay, let's go. Oh, by the way, I'm not going to, I want you to write it in your own words, the reason of why. That's why these are blanked out. There is something there for like the people who are at home to help them out. But I want you to put it in your own words because that's what's going to help things stick. So take a second and fill this blank in right here of why is it getting bigger. Based off what we just discussed, because those were together, that was the correct answer. Okay, now let's turn on our thinking brains again and let's think going to the left. Why is it, so talk with your table buddy for a minute, why would cesium be bigger than barium? Ready, set, go. Come up with a reason. Okay,
So-
stumped you all.
We're gonna.
Why would cesium be
We're
bigger
gonna
than
use our
barium?
science brain. Look at the science and think. Because
I'm putting that on a t-shirt.
okay.
Or send them to the website and then just feed around.
Yeah, just like on one side, Professor Science, and then there's one.
Okay, Cooper, I'm gonna pick up because I heard what you were saying and it was really good. Okay, everyone listen to this. So why is cesium gonna be bigger than barium?
So since barium has more protons and more electrons, then that means that they're more attracted to each other, so they kind of condense.
Perfect, right? I don't know where I'm at right here, but like barium, right, has 56 protons. Cesium has 55. How many, do they have the same number of rings? Yeah, because they're on the same row. So if you have the same number of rings, but you're increasing the strength of this magnet, it's going to start pulling this in a little bit tighter. Notice, it's not a huge difference, right? Compared to like up and down, I feel like changes more. But the stronger the nucleus, the stronger the Z, the smaller the atom will be. Questions on that why? Okay, take a second and fill that box in. Oh, I forgot to take gold today. Okay, everyone good? Okay, for a smiley face, okay, I'm gonna give you 3 elements. Just squeeze this in somewhere on your paper. Okay, just do it a practice problem of what you might see on the test. Okay, I'm gonna give you 3 elements. I want you to put them in order from biggest to smallest in size. Okay, so let's do.
you said that left to right, or like the ones that are right next to each other, they're not a big difference, but a small
Yeah.
difference. Okay.
Yeah, not a huge. And if you look here in the middle, it's like almost hard to even tell, right, if it's changing. Because all it is just one more, and so it just squeezes it. Yeah, good point. Okay, let's put iron, strontium, and oxygen in order from biggest to smallest. You can talk to your table buddy if you'd like.
Wait, strongest to what?
Biggest to smallest.
Biggest to smallest is gonna go.
Yeah, put them in order from biggest to smallest. And this is something you could see on the test. I'll give you a list of elements and you gotta sort them according to atomic radius.
She actually just did like right with the arrow. So just go strontium 38. Strontium, then iron 26.
Okay, if you get that one, try number 2.
Okay. Oh, she just gave us that little section there. Okay, so biggest is gonna be aluminum, then
When you're done, give me a pencil drop so I know you're done thinking. Big to small. If you did small to big, then just draw an arrow saying different string. Okay, let's go ahead and check your answers. You can have a smiley face for each one that you got correct. Okay? Alright, so I saw a lot of you doing this, and this is literally how you would answer the problem. First step is you gotta find where they're located on the table. Then you just look at the trend arrow and see where it lines up. So for the first one, we're looking at strontium, and then iron is there, and then oxygen is there, which I kind of created a diagonal for you. From going, did I say small to big? That's what I
Big
wanted.
to
Small, big to small. So biggest is gonna be farthest to the left and furthest down. So you should have strontium first. Strontium is gonna be bigger than iron, which would be bigger than oxygen. That's the correct order. Questions on that one? One smiley face. Yeah, one smiley face for the correct order. Okay, this one is I'm actually just looking at, right, there's just 4 of them. Like so. So, biggest, we want furthest to the left and further down. So, AL is gonna for sure be the biggest. I also know according to that, C is for sure gonna be the smallest. Now it gets a little tricky because now we have B or SI. One is further down, but one is further to the left. This kind of goes back to the point Rachel brought up. Since up and down changes more, SI is going to be bigger. Yes. Why is SI going to be bigger than B?
Because that's another ring.
Has a whole new ring, right? So even though, yes, like, it is pulling tighter, it doesn't matter, because you got an entire new ring on it. So things get in. Questions on atomic radius of the Y or the pattern. Keep in mind you'll be asked both types of questions. So it could be like the question I just asked that came answered of why is it this way, or it could be put them in order. Okay, next trend. The next trend we have is known as ionization energy. Now first off we have to understand what this is to be able to explain why it happens. Okay? Ionization energy is the energy it takes to remove an electron from an atom. This once again is a measured value. Scientists can do this in a lab. They can literally pull electrons off and measure how much energy it took to do so. Okay? The higher the ionization energy, the more it takes to pull it off. kind of a weird analogy that I think of is it's the cost of buying an electron. Okay, if I want to get this electron off, how much do I have to pay that atom in energy? Okay, so let's start by looking to the right. Okay, so as we look at our little chart here, and yours isn't color, well, it's not printed in color, I guess, unless you print it at home. But the red is high in energy, high in ionization, and then the blue is low. So generally speaking, as I look to the right, we see what's happening to ionization energy. It's increasing. Yeah, so that first blank right there, but increases.
What about like aluminum?
Good observation. So we do have some exceptions to the trend, right? Let's get to the why, and it might help us explain why every once in a while we have these dips in it. So, okay, turn to your table, buddy, and see if you can come up with a reason. Why, let's pick two to talk about. Why is it harder to pull an electron off of krypton than it is bromine? Ready, set, go. Come up with a reason.
Because it's because krypton has like stronger force keeping them together because there's more of them. They're all
Like look at
they are all very strong family bonds. It's hard to pull one of them out.
But if you're gonna create a new ring, then it's
Okay. Anyone willing to share their reason of why?
I have an idea.
Yeah, let's hear it, Rachel.
Okay, so I think it's because it's like harder to pull them off when there's like less of them, and if they're all on one ring, then it's like hard to pull off. If that makes any sense. So like, how like the last one, since they're like full rings, right?
Yeah.
And they're just like less than the row above, it's just harder to pull off, and like it takes more effort to squeeze it out.
Okay, you're on the right track. You're like, dude, so like if you understand in math, like proofs, you like have a correlation, but not the exact reason of why. There is a correlation that yes, the atoms that have a full octet are harder to pull electrons away from. But it's not the actual reason of why yet. But great thought, have a smiley face for sharing that. Anyone else have an idea? It all goes back to the force, right? If it takes energy to pull something off, it's because you're breaking some sort of force. The force that we're breaking is the force with the nucleus. What's different between the nucleus of krypton to bromine? Yeah, krypton has one more proton. One more proton makes a stronger nucleus, which means harder to pull that electron off, right? So it all goes back to always that idea of the force. In the end of this lesson, it should hopefully feel like the reasons of whys are all the same. Because it always goes back to that same pattern, okay? The closer the is to atom having a full octet, the more stable it is. No, that's not what I want you to write. I want you to put in your own words. I forgot my own thing. Okay? So it's all about the stronger the nucleus, the stronger the force, the harder it is to break. Or if you want to say it, more protons means more force, means harder to break. Once again, to get an electron off, we have to break that magnetic force. Okay, let's look up and down. Okay, so looking at vertical pattern now. Okay, so vertically, we see that as we go up, generally, ionization energy is increasing. Once again, there's always exceptions to the general rule. You don't have to memorize any of the exceptions. We're just focusing on the general pattern. So let's think about our reason why. Why would it be harder to take an electron away from krypton than from xenon? Turn your table buddy and say why.
Like what they're saying.
It's harder to pull off.
Yeah, it's like,
There's less
closer to
away
At the number of rings, can you see how
from
many
the
is
nucleus,
fit on one?
which means that the core is probably smaller.
Okay.
Before it's around.
It's hard to, I like hear good answers, but with masks on, it's hard to fully identify who said it to pick on it. But Jackson, I think you're on the right track. Are you willing to share with everyone?
Sure.
Thanks.
So since the ones lower have more rings, they end up further away from the nucleus, and so the force isn't as great.
Perfect. Yeah, great. Have a smiley face for that. It's all about distance here, right? The further it is away, the less attractive force there is to the nucleus, right? Because keep in mind, when we're talking about ionization energy, we're only removing the outermost electrons. So the farther those are away, the less force they feel, making it easier, right? Once again, no one be offended by this, but it's kind of like the difference of if, like, I'm the nucleus, okay, and you guys are all electrons, okay? If someone were to come and try to take Camille away, well, I'm, like, right here to stop them. But if they try to come take Rachel away, well, like, I'd have to hurtle over her desk and, like, you
Peace
know,
out, y'all. I'm out of here.
sorry, see ya. Right? Like, it's just that attractive force of distance, as well as we kind of have this problem too of shielding, right? Not only is she further away, but all you electrons in the middle also block that force as well. It's kind of like the idea of, like, if you've ever been to a concert before, and it's not like a stadium, but it's like flat. If you're further back, the sound actually gets blocked a little bit, right, from all the people in front of you. And that's kind of the idea with the nuclear force as well, is the inner electrons block some of that force from happening. So, very good. Jackson has a smiley face for that answer. Okay, third trend. Oh, do you want to do a practice problem for an everybody smiley face? Okay, let's do, I'm going to give you 3 elements, put them in order from lowest to highest in ionization energy. Let's do CO, and A, and F.
Do you want small?
Yeah, let's do small to big, or low to high. So lowest ionization energy to highest ionization energy.
Does the same rule apply for the ones next to each other? How it's like just by opposite?
Yep. Generally, yeah, it's not a huge change.
And when
Up and down gets much bigger, yes.
That's why these ones, when you throw them in water, they're so explosive. Because you just don't hardly need anything at all. You put them in water and they just give their electrons away. And I turn to like pretty much fire.
There you go. So yeah, the smallest ionization
The ones on the
energy
side.
is easy to take from.
The ones that if you throw them in water, they just explode.
Look at this graph.
You're saying the order of
Yeah.
Lowest.
So it's like they have like no ionization energy. You just put them in water and they ionize.
I don't know.
Yes. No,
Oh yeah, Francie.
Why would you
Yeah.
say?
Yeah, that's
CO
what I
or
was
D?
But with it, it has such a low ionization that if you were to put it in water, that's it. You're all gone.
So you kind of have to do a, like a, so you are right in general that going down affects it more than going across. You've got to look at the big picture too, of how much further across CO is from That makes sense. It's like when they're really close, like NH3, yeah, CA is gonna be higher. But because of those protons, cobalt has, right? So even though it does have some ring, it has 27 protons.
I relate to Francie.
So it is gonna be higher. Does that make sense? So, but it does get, and I won't have it, but it does get really tricky, like, well, what if you pick one that's like all the way down here versus like all the way up there? Won't ask you anything, or like hard to tell without numbers, so good observation.
Just hear us ranting about.
Okay, the correct order that you should have is NA is gonna have the lowest. Did I say low to high? You can already tell you. NA would be the lowest, then CO, then F. questions on ionization energies? Okay, third trend, electronegativity. Electronegativity has a similar feel to ionization energy, which is why, if you notice, the arrow is the same. It has that same diagonal arrow. The difference in definition, though, is ionization energy is about pulling an electron off an atom. Electronegativity is two atoms having a tug-of-war over it, but neither of them are actually winning. But you're wondering who's winning, who's holding on the tightest. So here's kind of how I visualize it. So when atoms bond, but they don't rip electrons off, like here's my nucleus of one. Okay, so there's my atom. Okay, what happens is when it bonds with another atom, their orbitals overlap with each other and they can share electrons. Now, if their ionization energy is really low, well then one of them just pulls the electron completely off. But electronegativity is about which atom has a stronger pull on that shared electron. So very similar in what's happening, just difference in definition. Okay, so generally speaking, what we see is as we go, when we're looking to the right, as we go to the right, electronegativity is increasing. Now, if you look at our little chart, though, there's something that's interesting. If I go all the way to the right, I don't know if there's a chart on your paper. Does anyone see what happens with that last row, last column, I mean? Yeah, they don't even have a ranking. Put a star, make a note of that. Any thoughts of why the noble gases, that's their name once again, why they don't have electronegativity values? Melody?
Well, they're completely full, like their shell's full, so they don't need to share anything.
Yeah, because this is all about the tug-of-war of sharing. They don't share at all. They never even share, so that's where they just get dropped from the trend. Because they just don't ever bond in this way. So, how's my based on Melody? Good observation. Okay, all right, anyone, I think hopefully you're catching the pattern. What would be our reason of why? Why would fluorine have a higher electronegativity than oxygen? I'm looking across the row. What's the reason of why? You have a thought? Yeah,
Because
Jacob.
it's more, like, the ring is more
Ooh,
cold.
close. So that's kind of what Rachel did. You have a correlation. But what's the actual thing pulling on the electron? The nucleus. What's the difference between the nucleus of fluorine and oxygen? Yeah, we got one more proton in there, right? So the more full they are, yes, they do pull harder because more things in the nucleus to pull from. So have a smiley face for sharing though, Jacob. The more protons something has, the stronger it can pull. Fluorine, in a sense, is the buffest atom on the whole table. Whenever they have tug-of-wars, if it's against fluorine, he always wins. P, G, whatever it is. Okay? The weakest is francium. Francium pretty much gives up every tug-of-war it's in. It just says, okay, here, have my electron. Right? Once again, going up and down. Why is it so easy to pull an electron off of francium? Or why is it so easy? Why does it always lose the tug-of-war? Yeah, Jack. So far away, right? I mean, francium has 7 rings. In order for that nucleus to attract another electron, like that's a huge distance to overcome. So kind of what we see, the general thing is the up and downs always go back to distance or rings. The left to rights always go down to that force of the nucleus or the Z, right? That nuclear charge. Questions on electronegativity? Okay, last one, and then we'll do our little puzzle game. Okay, last trend is known known as reactivity. So defining it, reactivity is the tendency of a substance to undergo a chemical reaction, either by itself or with other materials. Okay, so tells us how reactive something is, whether I have to store it locked up or if I can just store it on the counter, right? The more reactive something is, the safer we need to keep it. In general, what we see is that reactivity increases as elements get closer to becoming stable. Right? It's like they get anxious. The closer it is to having 8, the more it wants 8. If it's not very close to getting 8, then it's kind of like, oh, well, I'll get there when I'll get there. So with this one, it's interesting because we don't have a single like arrow. What we get is we get a split in the middle. Because, let me draw up here. Well, actually, I think I have one on the other page after we fill this in. I'll draw it on there. Okay, so what we see is that metals tend to like to lose their electrons. And so we see an increase on that side. Is everyone okay if I go to the next slide? Not yet. Okay. Can someone remind us where the metals are on the periodic table?
In the middle.
Good, yeah, it's everything left of that staircase, so the whole middle section all the way over. Okay, so everything where my little staircase is to the left is a metal. So those are the ones that typically give up their electrons when they react. Okay, non-metals tend to gain electrons when they react because they're all the ones on the right. And then of course the noble gases, that column 18, right, they just don't react really at all because they already have their stable configuration. Sorry, I'll go back to it. I just want to see if there's a periodic table. Another thing you can connect to with our valence, with our trend here, are the valence electrons. Right? So we said everything in this column has 1, these have 2, and then 3, 4, 5, 6, 7, 8. If the goal is to get a full shell, what we see is a split down the middle, pretty much. Right? So here's our staircase. About right there, kind of 3. Okay. Things that are close to 8 gain to get to 8. Things that are not close to 8 or less than 4 tend to lose. So here's our split arrow for reactivity. We get more reactive here, going that way, but also more reactive here. So the elements in the middle of the table are the least reactive. And these ones are very reactive. And then those ones up there are also very reactive. Which means if you want a really good reaction, you take one from here and match it up with one of the ones over there to get a really good reaction, because then they're both extremely reactive. Questions on that? Next time for our warm-up, I'll show you a demonstration in the lab of the reactivity of the alkali family. So we'll test and see, do they get more reactive, or they see how they get more reactive as we go down the column. Okay? All right, here's a summary of the different trends we talked about. If you want to just kind of put them all into one place. Just gonna draw it over here again. So on a periodic table, so that was not a very pretty periodic table. Okay? So for atomic radius, the trend goes like this. These ones are the biggest, these ones are the smallest. For ionization energy, let's get a different color. Ionization energy is the opposite. These ones are the easiest to take away from. Those are the hardest to take away from. So this means that has high ionization, IE, and then that would be the low end. Electronegativity is the same trend as ionization energy. So something that has a high ionization energy is also going to have a high electronegativity. Except you got to be careful. Remember, I kind of should have dropped, but the noble gases drop off on the electronegativity trend, right? They're just not part of it. And then the reactivity trend is the split one, right? Where it increases this way and that way from the middle. So keep in mind the middle ones are the least reactive. And the ones on the outer edges are the most. So what we're going to do for our assignment today, you have a good amount of time in class to work on it, which is what I was hoping for, is it's kind of like a little bit of a chemistry Sudoku puzzle. Okay, so go to your assignment packet and find the one that's called periodically puzzling. And I'll just give you a few words of some hints, I guess, words of encouragement. Okay. Go to that black basket right there. You should see a Unit 2 homework tab. You should just leave it there. Let me know if it's missing now.
We're entertaining enough.
Okay, so let me get a picture up here so we can talk about it together. Okay, so you have this blank periodic table. Line of rows, that matches. 1, 2, 3, 4. Yeah. Okay. Up top, it tells you a few things. Number one, if we look at the instructions, okay, it's telling us that each of these letters are representing an element of some kind. Your goal is to figure out where that letter fits on this periodic table. Okay? Now, one key thing that will either help you or hurt you if you don't pay attention to it is the fact that right there at the end of the instructions it says, note, the code letters fall into these groups on the periodic table. What does the word group mean when we talk about periodic tables? Columns. So they're telling us that J, Q, and K belong to the same column. Which means once you figure out where one of those letters go, you know the other two have to fit in that same column. It also tells me right away that these 3 letters can't be in column 1 or column 18, because there's only 3 of them and those ones have 4. Okay? Now some of the elements, as you go through the clues, don't have a clue about them. Because it's a process of elimination. Once you figure out the other ones, there will be a missing blank and you'll know it will fit there. So let's do one together to just get you started. Okay, so the code for the first letter V says V has the largest ionization energy in its period. Okay, so first off, what does it mean by a period? So now we're looking left to right. So it says it has the largest in its period. So looking left to right, which side has the largest ionization energy? Going this way. So that tells me that V belongs
Somewhere in the last column.
somewhere here. Now I don't have enough information to know where. So what I would do is I'd put it above to kind of keep track. And say, all right, I know V has to be somewhere here. Which also now tells me what?
That you know what group they're in.
good. So then I find the group of V, so who's in V's family, and I would write them also above column 18. I don't have a list, I don't know what they are. And know they fit somewhere here. So some of the clues will help you know left to right. Some of them will help you know up and down so you can find that spot. There is only one correct way to put this all together when you're done. Any questions? When you are finished, the way we will turn it in is you will turn it into Canvas, but I have it set up where you'll actually plug in your answers to a grid that looks like this to check it and see if you did it right. You'll have 5 attempts to turn it in. So if you turn it in, it won't tell you what the right answer is, but it will tell you which boxes are wrong. So then you can figure out what you might need to move around. Any questions? Hey, let me know if you get stuck. Ready, set, go. Talk to your table buddies. Help each other out.